This is part 1 of section 6.1, Vectors in a Plane. In this chapter, we're going to start connecting some of the things that we've done in trigonometry with some things that are done in coordinate algebra. And in this way, we're also going to connect how trigonometry is related to parametric equations. So in order to do that, we need to have a working idea of vectors. So this section is all about how we work with vectors, some of the basic operations, and some of the terminology that we'll need. So let's start with some different definition of vectors, some different parts of vectors. So the first thing is, there's two ways to represent a vector. One way is in component form. And what component form? It's an ordered pair of real numbers and it has components A and B. Now how we can tell a vector from just a regular ordered pair is we use little different symbols. And those symbols are angle brackets. This is the standard representation. And what this is known as is the arrow, when you see this, from the origin to the pair A comma B. So now when you see the angle brackets, you know that it is a vector as compared to just a point in space. And what makes the difference is not only is it a point in space, but it's also a direction as to how you got there. Now in our book, vectors are always represented from the origin, but they don't have to be. But the nice thing is you can take a vector, and let me draw one here real quick. You can take a vector in the coordinate plane, like let's say here to here like this, and what you can do is you can move it as long as you don't change its direction and length, that it's still the same vector. So our book goes ahead and just says it's from the origin, which is fine. Now what exactly is the magnitude of a vector? The magnitude of the vector is the length of the arrow. So that's the distance you've traveled. And the direction is which way the arrow is pointing. So vectors have length and direction. Now we do have something, because we're going to be working with vectors algebraically, we do have something called a zero vector, because we're going to be adding and subtracting vectors. So a zero vector is this vector. Another way to represent a vector is the zero vector is to put 0 with that symbol and arrow over it. And that's how another way we're going to represent vectors too that you're going to see. So just so you know, this vector has no length and no direction. The next term that we're going to be using a lot is the initial point. This is where the vector begins. Doesn't look like a C. And the terminal point is where the vector heads. And the reason I'm not putting ends, because the vector keeps going, it's an arrow. It's where it's heading. And equivalent vectors are vectors that have the same magnitude and direction. Helps if I can spell correctly. Now these words are going to become very familiar because we're going to be using them quite a bit. So those are the words that we need to explain our vectors. Okay, so now we have something called the head minus tail rule, or the HMT rule for vectors. So what it is if an arrow has initial point x comma y and terminal point, whoops, sorry, we give these ones because we're going to have two different x and y's. These will be ones. And terminal point, x2, y2. It represents the vector, and here's where the head tail thing comes in. You take the head where it's headed, and you subtract the tail where it's been, because the tail's behind the dog, in this fashion to get the new coordinates of your vector. Okay, so that's the head minus tail rule. So that's how, if you're given 2 points in space and you're asked to represent the vector that shows how you move from x1, y1 to x2, y2, use the head minus tail rule. Okay, so let's do an example here. So this is from page 464, number 1. What we're supposed to do is we are to prove vector RS, represented this way, and vector PQ, represented that way, are equivalent. Now this is the first time we've used this form of a vector. So what this is telling us is you have a vector that started at point R and passed through point S. So we represent it by those 2 points with the arrow on top. Same with PQ. It's a point that started at P and passes through Q. Now what we have to show is that they have the same magnitude and direction. So the coordinates of point R are -4, 7, and the coordinates of point S are -1, 5, and then P is at the origin, and Q is at 3, -2. Okay, so the first thing we have to do is find R and S. So that's going to be our head minus tail rule. So RS is going to be -1, its head, minus its tail. So it would be minus a -4, so that would be +4. And then again, its y coordinate, its head, 5, -7. And we can do the same thing for PQ. We're going to take 3 minus 0 and -2 minus 0. Now the nice thing about this one is you didn't really have to do that because P was at the origin. So Q really represents the head minus tail. So RS is going to be 3, -2. Oops. and PQ is just Q. So it's 3, -2. So you can see, oops, I said 2 and then I wrote a 3. You can see that they're going to have the same magnitude and the same direction. Because they're pretty much the same vector. Now if you were to graph them, and take a look at them originally, where their points were. So PQ would have been from the origin to the point 3, -2, which is like right there, so it'd be like that. And then RS was going from 4, -7 to -1, 5, like that. So this is where I was talking about that you can actually just take this vector and you would move it, and it would end up being right on top of the other one, the same length and direction. So they don't have to start at an origin, but for the most part we do that to do all the operations that we're going to do. Okay, so part 3 says magnitude of a vector, definition of magnitude, and that's a word we've been throwing around here. Okay, so if a vector v is represented by the arrow from x1, y1 to x2, y2, then the magnitude is, so when finding magnitude we use absolute value symbols because it's going to be positive. And how we can guarantee it's positive is that we're going to take the square root. So really what we're doing here is the distance formula. So we're going to take x2 minus x1 squared plus y2 minus y1 squared. So we're just using the distance formula. And that's how we can also guarantee that it's positive. So another way to look at this is you can say if V is represented by a vector like this, AB, then, because sometimes we just have the components, we don't have two different points, it's already, the head-tail role's already been done for us, so then the magnitude will look like this. So now what you're really looking at is the Pythagorean theorem, which is where it comes, the distance formula comes from. Okay, so page 464, number 5, a little example. We have these points. We have P, which is at -2, 2, and we have Q, which is at 3, 4, and we want to find the component form and magnitude. Of vector PQ. Okay, so the first thing we want to do is find vector PQ. So we're going to do our head-tail rule. So we're going to do 3 minus a -2, so that would be +2, and then we're going to have 4 minus 2. So we get, last time I checked, 3 plus 2 was 5, comma, 2. And then to find the magnitude of PQ, now you could have found that first and just used the first rule here, but since I have to find the component form anyway, which is this here, that's part of our answer, I'm going to just use the a squared plus b squared to find the magnitude. So I'm just going to have 5 squared plus 4 squared. So the magnitude is going to be the square root of 29, and that's the other half of my answer. Okay, so I'm going to stop the first part of this lesson here, and then we'll continue it in part 2.